Howdy, P-Chemsters. This is Mrs. Vanderley again in the second edition of the Blank Wall series of chapter 17. So we're at 17.2, standard reduction potentials. Again, what is this idea of a potential? We're talking about potential difference. We're talking about volts. So this section will kind of bring some light onto how do those voltages in your batteries, why are some of them 1.5, how do we get 9, where those numbers come from. And so they come from the ideas of these different metals in solution and how much reading, in a sense, will this voltmeter show. So we're going to be talking about measuring potential or measuring potential difference. Okay, so what again is measuring potential difference? This is the same thing as a volt. And so what again is a volt? We haven't really defined volt. We told you that the Volta guy in Italy came up with it, but what exactly is a volt? Well, a volt is defined as 1 joule per coulomb. And coulomb is given an abbreviation of a Q, I guess, because it sounds like coulomb. And so, well, hey, what's a coulomb? Well, this is a coulomb. His name is Charles Augustin de Coulomb. He was a French guy who was looking at this idea of charge. And so he's the one that defined what a coulomb was. So what is a coulomb? Well, it is a unit of electrical charge of roughly, get this, 6.241 times 10 to the 18th electrons. So if you gather up that many electrons and measure its charge, that would be 1 coulomb. And later on, in a later chapter, we're going to also see this again, where 1 coulomb is equal to 1 ampere times second. And we were going to use that knowledge when we talk about electroplating itself. So anyway, that's what a coulomb is. Let's go back to the other page now. So here we are, and how do they actually come up with these numbers? If we're going to find a potential difference, obviously we need 2 things to make a difference. So here we have, in this case, zinc and hydrogen. Hydrogen was very important because that's what they decided, that's going to be 0. That's an arbitrary decision saying we're just going to call the ability for hydrogen ion to be reduced, we're going to call that 0. So now they're going to take every other metal, every other ion, every other everything, and compare it to the hydrogen cathode here, because that's where reduction is taking place. And so in this case they put zinc in this salt bridge in this galvanic cell with the hydrogen, and whatever then the reading is going to be when you put zinc in here, and that will determine its potential difference, its reduction potential. So electrode, here we go, electrode potential is measured in reference to a hydrogen electrode which is arbitrarily assigned as 0 volts. And this is at standard condition. For gases, it's at 1 atmosphere. For solutions, it is a 1.0 molar solution and at 25 degrees Celsius. Now let's just kind of think about that for a minute. Because we have to define what a standard condition is, do you think that perhaps it will be different if we don't have a 1 molar solution? Let me think about that. Yes, that's the answer. So if it's at a different molarity, then you're going to have a different potential. So what do we do? How do we know that this is in standard condition? We have this naught sign. You see that little circle at the top of the E? That's called E naught. And that is to symbolize standard conditions. We saw that earlier when we talked about enthalpy. We had these standard conditions of enthalpy, like when we used Hess's law. So this should be nothing new. All right, let's go on to the next page. It says the diagram to the above illustrates what really happens when a galvanic cell is constructed from, it should be zinc nitrate and copper 2 nitrate using the respective metal electrodes. So what picture am I talking about? We'll flip back to the other page. I'm talking about this picture here. Notice I have a zinc electrode, and if this were in a 1 molar zinc nitrate solution, and notice I have a copper metal electrode and a copper nitrate solution. Let's just say that is a 1 molar solution. All right, and what is the voltage reading? I know it's kind of hard to read this scale here, but the very top of the arc is 0. And notice how this is right there is like a slash mark. That's a 1 voltage. And the arrow is slightly above that 1 voltage reading, and it's actually at 1.1 volt meeting. So the question is, how did the 1.1 voltage that end up on the voltmeter get there? Right, so I put the 1.1 volts here. By the way, volt is abbreviated with a capital V. I don't need to spell it out from here on out. So let's go back to the problem again. All right, so again, in the beakers, they need to have 1.0 molar solutions of the zinc nitrate and of the copper nitrate. Notice that the overall voltage was 1.10 volts for the process. And the question is, well, where did this 1.10 reading even come from? We don't have hydrogen there to look at. Where did the 1.1 then, how do we get that number from? Well, let's check this out. We have a reduction potential chart. The first thing to rest your mind, you don't have to memorize this. You'll always be given a chart like this. Phew. Notice something else. Look at this word right here, reduction. Remember what reduction stands for? Grrr. So what is reduction? Gain electrons reduction. Look at everything on this list. Do you notice that electrons are always on the reactant side? They're always on the left-hand side. That means that the fluorine gas is gaining 2 electrons. The silver +2 ion is gaining an electron. And so everything here is standard, where it's always a reduction chart. Now, does everything get reduced? The answer is no. In any kind of electrolytic cell here, that something has to be reduced, something has to be oxidized. But these are always written in reduction forms. So how do we do this? Well, let's see what it says down here. Elements that have the most positive reduction potentials are easily reduced. In general, these are your nonmetals. Do you remember way back at the beginning that nonmetals want to gain electrons, become negatively charged? And they do that to gain a full octet of valence electrons. So they like to gain electrons. They're going to be more stable, that the energy is actually reduced when you have that. What about this? The elements that have the least positive reduction potentials. Look way down over here. These are your negatives. They are easily oxidized. And what does oxidize mean? Wait for it. Wait for it. That's your Leo. Lose electrons oxidation. And so yes, your very, very active metals will actually want to lose the electrons to have that complete octet, to become more stable, to have a lower energy. So yeah, they're going to have these oxidations are actually written in reverse, and it says these are written as reductions, but lithium is probably going to undergo oxidation. Potassium will probably undergo oxidation. And notice that these are your very negative numbers. So then what? A table can also be used to tell the strength of varying oxidizing and reducing agents. Again, an oxidizing reagent is what is going to be reduced, and a reducing agent is what will be oxidized. So I can compare 2 numbers and predict which one is going to be the oxidizing one and which one is going to be the reducing one. And then letter D, it says, can also be used as an activity series. Metals having less positive reduction potentials are more active and replace metals with more positive potentials. Let's kind of give you an example of this. Kind of write small right underneath here. So what if I have zinc plus copper nitrate, copper 2 nitrate actually, and I'll make zinc nitrate and copper metal. Does letter D support this reaction? That's a single replacement reaction, if you notice. And will the more active metal replace less active metals? Will my zinc replace my copper? Let's find out. Metals having the less positive reduction potential are more reactive. Hey, let's find zinc on this chart. Oh, hey, I found it. Did you? It is right. Where'd it go? Right here. And then what? find copper being reduced. It's up at the very top. I need to scroll up a little higher to circle it. There it is. Okay, so does that statement back this up? So which one has the least positive reduction potential? That would be zinc at negative 0.76. And what about the more positive potential? That would be your copper at 0.34. So did zinc replace the copper? And the answer is yes. So now the zinc is in solution and the copper is now becoming its metal form. So yes, hopefully that makes some sense for you. Now, what else do you notice real quick? Remember the question above, where did that 1.10 volt come from? What do you notice about 0.34 and negative 0.76? I bet if you make the zinc into an oxidation, which it will do, the sign is going to change. And so when zinc is oxidized, it's positive 0.76. And then copper, as is, as written, as 0.34. What will happen if I add those two numbers together? I bet you get 1.10 volts. We'll talk about that shortly. All right, so here's problem number 2. Using table 17.1, place the following in order of increasing strength as reducing agents. Remember, what is reducing agent? That which will undergo oxidation. That will be the more negative or the less positive of all. So find each of these in the chart. It may take you a little bit until you get familiarized with it, and find out which one is more likely to undergo oxidation, and keep letter B in mind as you do that. So I'm going to pause this while you figure it out, and then I'll join you in a minute. Okay, well, hopefully you found the numbers associated with each one of those. So I found K and found it to be negative 2.92. I found iodine to be 0.54. I guess I'm going right to left. Water is negative 0.83. Hydrogen negative. Notice there's a negative there, by the way. 1.60, 2.87, and 0.52. So how do I answer the question? If those are the reduction potentials, what would happen if I made those into oxidations? Well, the signs would actually be reversed, and then I can look at, well, which one has the highest number? And so the one that is the least positive reduction are going to be the easily oxidized. So just once I wrote those numbers down, then it gets pretty obvious on the ranking. So most negative is potassium, and then I got the water, and then I found the copper ion, and then I found the iodide. Now notice that the iodine is a non-metal, which makes sense. And then the hydride is a non-metal as well. And then the fluoride. Hopefully the fluoride ion makes a whole lot of sense. Does it really want to undergo oxidation? Fluoride, F negative. Will F negative lose another electron? Have you ever seen such thing? There is no way. That is not going to happen. Fluoride will not become F negative 2. I'm sorry. So that would be the worst reducing agent because it does not want to be oxidized. All right, let's go on to the next page. All right, so how do we actually go about calculating this? I've sort of insinuated how to do this. This potential is actually symbolized by a variety of things. I typically stuck with the very first one, the capital E naught cell. But if you ever see it written down in a book or in a problem, if it's an EMF, which is electromotive force, or that little squiggly E, that's a Greek letter, believe it or not, they're all saying the same thing. So what you have to do is decide which element is oxidized or reduced using the table of reduction potentials. The more positive reduction potential is going to be reduced. Hopefully you've already figured that out. Write both equations as is from the chart with their voltages. Reverse the equation that will be oxidized and change the sign of the voltage. Balance the two half reactions, but this is key. Do not multiply the voltage values. Add the two halves together, and voila, there's letter F. So go ahead and do problem number 3, and when you are done, go to the next blank wall series. We'll see you later.